With each fascinating picture captured by the James Webb Space Telescope, it continues to gather contemplations from various corners of the universe, including planets within our own planetary system. A year earlier, we reflected on our most significant brief sea pictures showing the Kina Nebula, the Saint Quintet, and, most strikingly, the enchanting Deep Field image. This particular picture clearly depicts different galaxies resting in the vast expanse of the universe, fulfilling the doubts raised. The James Webb Space Telescope hasn't stopped being a marvel. It has, in fact, uncovered objects that challenge deeply grounded cosmological hypotheses. These astonishing revelations are now being named universe breakers by cosmologists, frustrating established experts with their ability to challenge existing theories. The reasons for these discoveries remain shrouded in mystery, throwing our theories and hypotheses into disarray. So, what's the latest scoop from the James Webb Space Telescope? What remarkable new discovery has it revealed that was previously unknown to us? Join us as we dive into the revelations of how the James Webb Telescope has presented evidence proposing the presence of another universe, testing the standard understanding of the Big Bang. Our universe, as we've long known it, arose from a hotter, denser state through a theory known as the Hot Big Bang. This groundbreaking scientific achievement gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, an echo from the early, hot, and dense state of the universe. Over time, the Big Bang has remained the leading theory explaining the origins of our universe. However, new and fundamental insights have led cosmologists and astrophysicists to re-examine both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, with the prevailing theory of the universe's origin enduring. According to the dominant view, the universe began as a smaller, denser entity in the distant past. The presence of radiation, such as photons, shows that the universe was hotter at its beginning and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels varied, creating conditions where a singularity could form and the laws of physics would break down, around 10 superscript 3 seconds after the beginning. In such a short span of time, microscopic distances, short timescales, and high energy levels challenge our understanding. Rewinding the cosmic clock to this speculative zero point, if the universe began as hot and dense, it would have expanded and cooled, producing vast amounts of particles and antiparticles. Excess particles would have been destroyed by radiation as temperatures decreased. The breakdown of the electroweak and Higgs forces led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent expansion due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. About 380,000 years later, the discovery of the cosmic microwave background confirmed the Big Bang theory as the most supportive explanation for the universe's creation, describing the early universe as a hot, dense soup of subatomic particles gradually cooling over time. The Big Bang versus steady-state theory. While most cosmologists and astrophysicists embraced the Big Bang theory, staunch defenders of the steady-state theory, such as Fred Hoyle, continued to support increasingly doubtful ideas, only to face defeat in the face of overwhelming evidence. The proof presented was conclusive. It wasn't dimming starlight or reflected heat from dust. The celestial glow displayed remarkable consistency, resembling a perfect black body yet having no connection to known objects in the universe. Despite this, Hoyle and his allies continued to undermine scientific progress by backing scientifically dubious ideas. Meanwhile, space science and cosmology underwent significant changes from the 1960s through the 2000s. We mapped the universe, described its large-scale structure, and examined the evolution and dynamic interactions of galaxies and their stellar populations. Yet, even with these advances, anomalies emerged that challenged explanations within the framework of the Big Bang theory. Most notably, the absence of predicted relics, such as magnetic monopoles or particles from grand unification, which led many to reconsider aspects of the theory. The universe we observe today seems to require forces beyond our current understanding. Challenging current theories, inflation and beyond. Despite these challenges, the expansionary model persists. Two approaches have emerged: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang viewpoint. Inflation suggests a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns, reinforcing its validity. However, despite alternative theories, inflation's scientific strength remains unmatched. Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the earliest moments of the universe. Recently, efforts have been made to challenge the authenticity of inflation theory by supporting conformal cyclic cosmology. However, this theory is inherently flawed, as its predictions differ significantly. Conformal cyclic cosmology proposes that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang era. James Webb Telescope's amazing discoveries. Astronomers quickly noticed anomalies in the images sent by the James Webb Space Telescope, JWST, starting in 2022. These revelations could require a reassessment of key aspects of the universe's origins and development. One major discovery made by the Webb telescope was the presence of fully developed galaxies much earlier than predicted by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes were thought to form first, followed by galaxies. Such discoveries disrupt our understanding, like encountering grandparents depicted as children in a story. Furthermore, later evidence revealed irregularities within major theories of the universe, such as the persistent error in determining the Hubble constant, which remains unresolved despite improvements in data accuracy and measurement techniques. New data from the Webb telescope presents challenges to the current cosmological model, highlighting imperfections and raising questions among researchers and physicists. While the model has been adjusted recently to align with emerging data, some argue these changes have been too accommodating. As a result, there is growing recognition that a shift in perspective may be necessary, possibly reshaping our understanding of the universe's fundamental properties. A shift in cosmological understanding. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the detection of the cosmic microwave background radiation in 1964, confirmed the Big Bang as the most plausible explanation for the universe's beginnings. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of infinite expansion, introduced in 1981, was proposed to resolve anomalies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, exceptional expansion shortly after the Big Bang. However, new challenges arise, particularly given the prevailing belief in the existence of a single universe. Perhaps, there are countless others beyond our observational reach. Some observable anomalies, such as singularities within black holes, find support through indirect evidence. However, the stunning discoveries of the Webb Space Telescope, regarding the unexpected development of galaxies and the ongoing issues with the Hubble constant, raise concerns that we may be approaching a tipping point where a major revision of our current cosmological model becomes essential. This could necessitate a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. The intersection of consciousness, quantum physics, and cosmology. Cosmology, unlike many other scientific fields, grapples with fundamental questions about the universe, its origins, and our place within it. The study of consciousness and quantum physics also investigates similar topics, examining the intersection of theory and reality. It is crucial to scrutinize these foundational assumptions, given the impact of theoretical presumptions on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to significant changes in societal perspectives. A similar shift in our understanding of the universe may be approaching, driven by an impending scientific revolution in cosmology. Scholar Robert Anton Wilson argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers. Investigations into cosmology may eventually lead to the breakdown of the current model, not due to observational errors, but because of its inability to embrace new principles that fully reflect the latest discoveries. A new cosmic revelation. The search for another universe. As the James Webb Space Telescope continues to uncover revelations that could forever alter how we understand the universe, renowned astrophysicist and science communicator Neil deGrasse Tyson has made headlines with remarks on the telescope's potential to challenge established scientific understanding. Launched in December 2021, the JWST is a powerful space telescope designed to explore the universe in infrared frequencies, allowing scientists to peer farther into the cosmos than ever before. Tyson's comments stem from the extraordinary discoveries the telescope is already making, particularly in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson has not directly claimed that the JWST has found evidence of a parallel universe, he has referred to some of the astounding and unexplained phenomena observed by the telescope, which could suggest the possibility of something beyond our current understanding. One such anomaly is the presence of strange, unexplained patterns in the distant universe, which may suggest that the laws of physics as we know them could be different in other regions of space, or that the universe itself could be far more complex than previously imagined. This could imply the existence of multiple universes, as proposed by some theories in cosmology, such as the multiverse theory. However, it is important to note that while these observations are intriguing, they do not yet provide concrete evidence of another universe. Instead, they open up possibilities for new theories and ideas that could redefine our understanding of space, time, and reality itself. Unveiling the future of cosmology. As the James Webb Space Telescope, JWST, continues its groundbreaking mission, it is clear that humanity stands on the brink of a new era in space exploration and cosmology. The data collected so far has already begun to challenge existing models and hypotheses, forcing scientists to reconsider some of the most fundamental principles of physics and cosmology. One of the most exciting aspects of the JWST's discoveries is its ability to observe the early stages of the universe with unprecedented detail. Its capacity to detect infrared light allows it to peer through cosmic dust clouds, revealing distant galaxies, stars, and other celestial objects that were previously beyond our reach. These observations have opened new questions about the timeline and processes of cosmic evolution. The telescope's findings suggest that galaxies may have formed much earlier than previously believed, challenging the long-standing view that such structures took billions of years to develop after the Big Bang. The discovery of ancient galaxies raises profound questions. How could such complex systems have emerged so early? Were there unknown forces or conditions at play in the early universe? Redefining cosmic timelines. These early galaxies are not just anomalies. They are evidence that something fundamental about our understanding of the universe's formation might be incomplete. If galaxies could form so soon after the Big Bang, perhaps the conditions of the early universe were far more hospitable to rapid structure formation than scientists ever imagined. In addition to observing ancient galaxies, the JWST has also provided groundbreaking insights into exoplanets and their atmospheres. The ability to study the chemical compositions of distant worlds represents a major breakthrough in the search for extraterrestrial life. By analyzing the light passing through an exoplanet's atmosphere, scientists can identify specific molecules such as water vapor, carbon dioxide, and methane, clues that could reveal the potential for habitability beyond Earth. Some of the exoplanets studied by the JWST show unexpected features, including unusually high levels of methane or other compounds difficult to explain using current planetary formation models. These anomalies suggest that our understanding of planetary chemistry and atmospheric evolution might also require revision. The multiverse. Science fiction or scientific reality. Perhaps the most thrilling implication of these discoveries is the possibility that the universe is not alone. As the telescope uncovers more anomalies, scientists are beginning to consider theories that were once relegated to the realm of science fiction. The idea of a multiverse, multiple universes coexisting alongside our own, could gain scientific traction if observations continue to reveal phenomena that defy the laws of physics as we currently understand them. If different parts of the cosmos follow distinct physical laws, it could suggest that what we perceive as a single universe is just one part of a much larger, more complex multiversal reality. This radical shift would fundamentally alter our perception of space, time, and reality itself. It could redefine our place in the cosmos, suggesting that countless other universes, each with unique laws of nature, exist just beyond the boundaries of our observable reality. The mystery of dark matter and dark energy. The potential for the JWST to detect signs of dark matter and dark energy, the two most mysterious and elusive components of the universe, could unlock answers to some of cosmology's biggest questions. Dark matter, which is thought to account for roughly 27% of the universe, remains invisible and undetectable by conventional means, yet its gravitational effects shape galaxies and influence the large-scale structure of the cosmos. Similarly, dark energy, believed to drive the universe's accelerating expansion, makes up approximately 68% of the cosmos, yet its true nature remains one of the greatest unsolved mysteries in physics. If the James Webb Telescope can provide insights into these enigmatic forces, it could lead to breakthroughs that revolutionize not just cosmology, but also quantum physics, fundamental mechanics, and perhaps even our understanding of consciousness itself. The dawn of a scientific revolution. As the telescope continues to push the boundaries of discovery, we may be witnessing the beginning of a new scientific revolution, one that could forever change our understanding of the universe. Just as the discoveries of Copernicus, Newton, and Einstein redefined humanity's place in the cosmos, the JWST's findings might herald a similar paradigm shift. Already, its revelations are forcing scientists to rethink established theories, develop new models, and question assumptions that have guided cosmological research for decades. As groundbreaking as these findings are, they likely represent just the beginning. The more we uncover, the more profound the questions become. What if the Big Bang wasn't the beginning of everything, but just one event in an endless cosmic cycle? Could there be evidence of ancient civilizations hidden within the distant galaxies now coming into focus? What lies beyond the observable universe, and